All right, folks, it's Bass Action back in action here. In this video, we are going to talk about three things. We are going to talk about how the set of real numbers is broken down into some different categories. We are going to talk about how to write our answers in interval notation instead of this inequality notation that you've done in the past. And then we're going to do a quick review of some properties and categorizing those because they're words you haven't probably reviewed in a long time. All right, so let's start up here on the top on our real numbers. Now, a couple things that I want to point out here is that in this big set of real numbers, this is going to include all of the numbers except things that are imaginary numbers, so anything with an I. So if it doesn't have an I, it's going to fall into this big category. Now, this big category is broken down into two things. It's a little bit hard to see here. There is this little dividing line here that is going to separate our values between our rational numbers and our irrational numbers. So the irrational numbers are things like roots that maybe don't simplify down to a perfect square. So square root of 4 would be a 2, that doesn't count. But square root of 3 is just going to give us a decimal. Of course, we could do, let's say, the fourth root of 5. That's also not going to simplify into anything nice, so it would be irrational. And then we have things like pi and that number e that we've seen in the past. So in general, these are going to be our irrational numbers. Now, rational numbers do have a specific definition. They are any number in the form a over b, where a and b are integers. Okay, so a and b are integers. So before, I'm going to skip away from this for just a second, and I'm going to come over here, and I'm going to talk about the integers. The integers are a subset of the rational numbers. So these would be our integers. Now, the integers are going to be our positive and negative whole numbers, but it also includes 0. So we could have -3, -2, -1, 0 is included. Then we could continue on to the positive side, and of course it would go in each direction, positive and negative. So if these are the integers, rational numbers are any number that can be written using two integers. So an integer over an integer. So an example of a rational number is, let's say, 1/3. Now, sometimes students want to think that 1/3 is irrational because it does go forever, but irrational means that it goes forever without repeating, and 1/3 is repeating. It is also, from our definition, an integer over an integer. Now, if we then look at subsets of integers, we've got a subset in here of some numbers that are subsets of that, and those are going to be our whole numbers. So technically, the whole numbers are only the positive integers. So these are going to be only positive integers. So those are going to start with 0, 1, 2, 3, 4, and so on. So those are going to be our positive whole numbers, but we're going to include 0. It is important to know that 0 is not technically positive or negative, but the whole numbers include positive integers, including 0, and then keeps going. Now, the next one that we're going to look at, or I should say our last one, is going to be what we call our natural or the counting numbers. So sometimes these are called counting numbers because when you were little and you first learned to start counting, you didn't probably learn to start counting at 0, you learned to start counting at 1. So the natural or counting numbers start at 1. So you do want to be comfortable being able to categorize numbers into these different areas. The next thing that we're going to look at is looking at writing things in interval notation. Now, your Algebra 2 teacher may or may not have had you do this, so we want to make sure that everyone is comfortable with this. When we are working with our intervals, we are going to have two different types. We are going to have what are called bounded intervals that will have a clear beginning and an end, a finite beginning and end. And an unbounded interval is going to be, just as it sounds, unbounded. It's going to go forever in one or both directions towards infinity or negative infinity. Now, when we are trying to learn how to translate our inequality notation to this interval notation, a good little thing to do in the beginning, as we're just learning, is to make a little graph or a number line. So if I make a little number line here, I can put my arrows on the end. I don't need to put all my numbers on it. I just need to take the two numbers that are on my inequality and put them on the number line in their numerical order. So -4 and 3. Now, what we want to point out here is that if the inequality sign is not inclusive, when you write that graph, remember, we make those open circles. So the non-inclusive inequality becomes an open circle, and the open circle for the interval is going to become a parenthesis. So since I have two open circles, these will both be parentheses, and then I just take the numbers and I put them inside. Be careful, because we have to read this in the context of the problem. This looks like an ordered pair right now, but it is not. It is an infinite number of numbers between, or an infinite number of values between a -4 and 3. But we do not include the negative in 4 and 3. So now these start to go fairly quickly. I'm going to take my values, 10 and 15. Notice now that the 10 and the 15 are inclusive, so we recall that those are solids. Now, solid closed circles will become square brackets. We do have to be very careful on our notation. Make sure that they are clear. Then we're going to have what is called half open. So this is called open because both of them are open. This is closed because both are closed. And half open means that one will be open and one will be closed. So now we're just going to have a mix. So again, these go pretty quickly. You'll eventually not need to do any type of little graph in the middle, but it's a good thing for now. So I've got my open circle, my closed circle. Now I can easily translate that to a parenthesis and a nice square bracket. Now, down here, we're going to have our unbounded intervals, and these are going to go to positive or negative infinity. We can still draw a little graph. I'm going to put my 5 on here, -5. It's inclusive, so I'm going to make it closed. And when I read the inequality, I read from the variable. X is greater than -5, so my arrow goes in that direction. Now, when I write this interval, the closed spot, the closed value, is it still a bracket. And then I go to infinity, and notice up here, we are never going to use a square or a square bracket with our infinity. So this will always be a parenthesis. So I'm going to do another one, 6. This one's going to be open. This is why it's called open and unbounded versus closed and unbounded. This is going to be less. So now I'm going to have negative infinity to 6. This has to be open or a parenthesis, and then my open circle is also a parenthesis. Now, our all real numbers in the past, you would have done that. You would have done your 2 vertical lines with making it look like an R with 2 vertical lines. Our new notation for that is going to be negative infinity, positive infinity, and then 2 parentheses. The last thing that I want to note is that every single time you write something in interval notation, it must be from low to high, reading left to right, low to high. This answer, for example, would not make any sense if I wrote it 15, 10. That would never be correct. It has to be 10 to 15. All right, the last thing that we're going to look at are some properties. You haven't seen these probably in a long time, so I want to talk about these. I'm going to do these in a little bit of, I'm going to kind of bounce around and talk about these, and I want you to look at our, sorry about that. Okay. I want to take a look at our names up here, and I want you to see that I've got 2 things here that are called identities, okay? I have a multiplicative identity and an additive identity. An identity should be something that I can add, in the case of the additive, to a value or multiply a value by that will result in the original value staying the same. So what can I add to any number that will result in the number not changing? And that answer is 0. So if we look down here, we're looking for somewhere where I have a value plus 0, and it's right here. So this is going to be the additive identity. I'm just going to abbreviate these. The multiplicative identity, what can I multiply? What number can I multiply any other number by without changing it? And the answer is 1. So we're looking down here for somewhere where I've multiplied something by 1, and that's going to be right here. This is going to be the multiplicative identity. The next one that I want us to take a look at are the inverses, okay? So we're going to have a multiplicative inverse and an additive inverse. An additive inverse is going to be adding something to a value so that my answer is 0. So I'm looking for somewhere where I've added two values together and I was left with 0. Now, I can find that right here. So my x plus my negative x, so the negative value of any, or the negative value of any other value when you add them together is going to give you 0. So this is our additive inverse. The multiplicative inverse is going to be when I multiply two things together and I'm left with 1. So that's going to be right here. When I multiply anything by its reciprocal, it's going to give me 1. So this is our multiplicative inverse. Those are definitely words that students often don't remember. Now, next thing that we're going to look at is the commutative property. The commutative property just says that we can either multiply in any order or we can add in any order. So this would be commutative because a times x is the same as x times a, and then this would also be commutative because x plus 9 is the same as 9 plus x. The next thing that I'm going to have us take a look at is going to be the distributive property, okay? And that simply means that we can take a value and distribute it over parentheses. And I've got two examples of distributive here. I've got a distributive here, and I have a distributive here. Now this one is the easier one to recognize because what we're distributing is in the front. This bottom one is a little harder to see for some. We can think of it as distributing that 7 backwards. That leaves us with our last one that we're going to look at, and that's going to be the associative property. And you can think of this as grouping, okay? So right here we've got our grouping. This is the associative property. Can think of that as grouping. So 7 times x times y can just be grouped. I can group these two and then multiply y, or I can group these two times the 7. We can also do that with addition. Addition also has an associative property to it. And we can see that x plus 7 plus 9 can be grouped differently and we still get the same result. Okay, that's everything that I've got on this page, and we will work more with these properties and labeling things in this manner in class.